Let me just start the introduction to the next presentation, which is application of geoscience metadata for machine learning classification of seismic interpretation by Tonje Braut and Thomas Grant. Tonje is a geoscience software analyst. She has been with Cegal for almost 3 years. She has been working on the support desk where some of you may have communicated with her already. She is now working in the data management portfolio team in our headquarters in Stavanger. And Thomas is a senior data and digitalization consultant. He's been with Cegal for almost 3 years as well, working as a data science expert advisor. Thomas is helping out with data science across our organization. And now I will give the word to Tonje, who's going to start out this presentation. Are you with us, Tonje?
Yes.
Yes.
Yes, I am. Thank you, Renee. I hope you can all see my screen okay.
We can. Thank you.
Yeah, perfect. So, hi everyone. Thanks for joining in and welcome. My name is Tonje and I will be taking you through the first half of this presentation today. So what we'll be covering is how you can take advantage of the different metadata that is generated by your geoscience applications. And we'll be focusing today on seismic interpretations generated by Petrel. So we'll be showing you how you can collect and consolidate information from your seismic interpretations. And then my colleague Thomas will take you through a demo of a machine learning experiment that was used to do a quality assessment of this data. So before we kick off, I'd just like to give some credit to the creators of this work, my colleagues Ketil Vågbø and Hilde Tveit Haaland, who were able to implement the workflow we're about to show you successfully at the client site to collect information and quality assess seismic interpretations from thousands of Petrel projects. So the agenda for today is we'll discuss a bit about what geoscience metadata is and different challenges with working with application data. Espen has already talked a bit about this. We have a use case for you where we would like to find the best seismic interpretation from a list of thousands of Petrel projects. And we have a solution proposal for that. We'll show you some examples of how you can browse the information you collect in Arcgis and Power BI. And finally, Thomas will do the demo of the machine learning experiment that was implemented in Python. So let's just jump right into it. What is geoscience metadata? Simply put, metadata is just data that describes other data. So in our case, where we're focusing on seismic interpretations, that would be information about the interpretation itself. So do you have a 2D or a 3D interpretation? And who was the original interpreter? Do you maybe have multiple interpreters? For 3D grids, which seismic survey was used? Which seismic cube was used? Do you have any information on the lateral extent or the coverage of all your interpretations? And maybe you'd like to find some information on the numerical attributes. What are your minimum and maximum values of your picks? What are the point densities of the different interpretations, or the compactness? So there are quite a few applications available that generate different geoscience data objects. We have Petrel, Decision Space, Geoteric, Paleoscan, and several others. And what they have in common is that they provide the users with a great deal of freedom. You can easily create objects, create your own interpretations, and get going with picking on any seismic cube you have available. And users are free to save and generate as many data objects as they please. Typically, these geoscience applications would have been used in an organization over quite a great period of time. And in some companies, we may be talking about decades of usage, which then leads to data accumulation over time. So we have a great deal of data, we may have a great deal of Petrel projects, but how can we take advantage of the data we already have? So just to show you an example of what the data accumulation may look like in any given organization. So for instance, you have a company that's been using Petrel since the early days, since its release in the early 2000s. And just by organic growth, you can see quite a steep increase in number of projects over time. And the graph also shows a very steep increase in number of projects, which could be a result in data acquisition or a data merger between different companies. And the thing to note here is that this just shows the number of projects you have for an application. You also need to consider the vast amount of data that each project may contain. Which brings me into the challenges of working with geoscience applications. And as we've already touched upon previously, is that many of these applications generate proprietary files. And the files that are generated are usually not readily accessible for users outside of this application. Sometimes, for instance, with Petrel, if you want to have a look at a project and what it contains, you would need to execute the application and open a project to see what's inside. Or in some cases, there are special APIs. Taking Petrel as an example again, the Ocean API that allows you to build Petrel plugins. So there may be tools available that can grab the data for you. In addition to this, there's usually also a lack of data management governance for data generated from these applications. And normally, you wouldn't really have a very good control over which version of any given data object that was used to make any decision. So you might have had this information at the time the decision was made, but over time, this information can easily get lost. Moreover, there's no usage standard for all of these applications across companies. And as mentioned, there's a lot of user freedom. So a user can set a project to whichever coordinate reference system they please. They can name objects as they please and set the units to their likings. So all hope is not lost. There is a way to mitigate this, and prevention is usually the best way to go. And take actions as you see problems appear or before they appear. So by implementing good data governance procedures, you can avoid any problems to arise. And by making sure that the end users are well trained and aware of what issues you may face with data consolidation if you don't manage your projects and data properly. And there are also tools that can track and monitor the application data usage, such as our Blueback project tracker, which we'll talk a bit about later. There's also a way you can make the information more readily accessible for users and data managers by building a metadata index where users can search, filter, and find the data they're after. And again, Project Tracker is a tool that can help you do that for Petrel projects and Petrel data. So that takes me into the use case that we want to present to you today, and back to the figure that we looked at earlier. So we have an oil company that's been using Petrel for a number of years, and they have thousands of Petrel projects lying around on disks. And there's also been a few mergers over the years. So we have a full network of projects with a lot of data we don't know the quality of. So the question is then, how can we find this and what do we have? So some challenges with working specifically with interpretation data and Petrel is that there's no consistent naming convention, and usually some companies have proper conventions for naming objects in projects and some don't. What we need in this use case is a consistent naming convention for seismic horizons, surveys, and seismic cubes. What you may also encounter are spelling mistakes, which makes it difficult to properly match the names of your horizons. And you may also have several copies of the same interpretation grid that have minor or no differences at all. Additionally, there may be quite a few scratch pad interpretations where you may only have a few inlines or crosslines interpreted, which would give you close to no value at all. And lastly, the use of tagging, for example, Petrel quality attributes to mark final data hasn't really been readily used across companies as well. So the workflow we propose to solve this and to identify what type of seismic interpretations you have across your projects is to scan your Petrel projects using the Blueback project tracker. This will scan your projects and send the information to a SQL Server database. Then to define a standard naming convention for your seismic horizons, surveys, and cubes, and map these to the interpretations you already have in your projects. Then we would like a way to browse or view the data with other applications, and on top of this, extract this information so that it can be used for machine learning and quality assessment. So let's have a closer look at this workflow. As mentioned, we used Blueback Project Tracker to scan the Petrel projects. Tracker will crawl through your file system, locate any Petrel project folder or Petrel project file, open this, and extract the contents of the project. This is all then written to a SQL Server database. So for interpretations, we can also extract spatial information, and we can also export images, georeferenced images of the interpretations in your projects. After the scan, the Blueback project tracker can be set up to run the name mapping. So this is done by using a fuzzy text matching algorithm that will then take into account any spelling mistakes or synonyms and map and name your horizons consistently. All of this is then stored in a SQL Server database where you can access it from any applications that can read data from a SQL Server database, such as ArcGIS Pro, Power BI, or Python, as Thomas will demonstrate. So just to give you an example of the name mapping. So say you have a project with, or multiple projects with different variations of the formation name Oscar. These will all then be identified as the same horizon name, and the horizons will then be tagged in the database with the name Oscar, so you can easily filter and find the horizons you're looking for. Similarly with seismic surveys, these can all be mapped to standard names as well. So the metadata that we store for interpretations are all listed here. I won't go into much detail on each of these, but it's worth mentioning that we do collect some numerical attributes that may be helpful later with the quality assessment. So that would be the lateral extent, the compactness, the point count, and the area of your interpretation coverage. We also collect some basic information such as project name, the last modified date, last user, etc. So I will show you some examples where we have gathered this data and imported to ArcGIS and Power BI. And Thomas will then take over to show you how this information was used to do the machine learning classification for interpretation quality. So I have an example here of ArcGIS where you can see a map, and the interpretation information that we've collected from the Petrel projects are easily exported as a query layer. This makes it easy for you to get an overview of the coverage of your data, and you can easily filter through the attributes to search for any interpretation of your interest. So you can, for example, highlight an interpretation in the attribute list, and it will zoom to that area, and you'll be able to see a clear outline of the polygon that was generated during the tracker scan. And as you can see from the attribute list, we're also using the mapped names, standard names from the name mapping process. As I also mentioned, the Blueback project tracker is also able to export georeferenced images of the interpretations located inside your Petrel projects. These are easily imported into ArcGIS, where you can view them side by side with your polygons. And you can grab in multiple interpretation images at once to give you a good overview of the quality of the interpretations. And I have an example here as well with a custom Power BI setup where we've implemented a map plugin. So you can also bring in your interpretation data from your tracker database here. This allows you to set up easy queries to filter on any attributes of interest. So in this case, it's set up with the mapped names for stratigraphy groups and stratigraphy, surveys, and cube names. So by filtering on stratigraphy, you can easily zoom into the location of your interpretation on the map, and you can use the links to view your interpretation images in Tracker Web. So all of these features are now available with our latest release of Blueback Project Tracker, and it's available now from OceanStore to all clients. So with that, I will hand the word over to my colleague Thomas, who will take you through the Python demonstration.
Yeah, I hope everyone can see my screen okay. Good morning. My name's Thomas Grant. I'll be going through there we go. I'll just be going through the machine learning and Python side of the Evergreen Maps project. I'm standing in for Hilda Borland, who was doing this work. I'll just go you through some of the examples and of how the work was done, show a little bit of the Python coding, and how this workflow was done. So I can see a little image here of one of these interpretations. So as Tonje just explained, most companies will probably we developed quite a large database of seismic interpretations. So we saw from that graph that there were, example, that there were thousands of different control projects, each of which could have several different interpretations within them, different vintages, and so on. So we roughly ended up with thousands, if not tens of thousands of interpretations within a single database. And this they can be quite old, some of these interpretations, so it's quite a task to be able to identify which interpretations are good or bad. So that's really the aim, to provide some sort of label to give an indication of whether each of these interpretations in the database are either somewhat good or bad. And that way you can have a sort of best examples from different locations, for example, to having a database. Otherwise, you'll be looking at just simply too much data. Also want to automate this process to be able to manually go through all of those projects or all of that data from the database, for example, in the Power BI report, and actually manually label every single interpretation would be an extremely slow and also boring process. You don't want to tie up your domain experts clicking through classifying each of the interpretations as good or bad. That's just not very feasible. So we want to be able to automate this process, and we can show that we can do that using both Python and machine learning. So the aim really is to complete this workflow, but to save time, and that's by automation. This is particularly great in the case of a merger. Say you have two companies joining, merging their data sets, you suddenly have a lot more data and you want to streamline everything into sort of one experience. So Python, generally lingua franca in terms of data science and machine learning. It certainly is a pretty popular language in Cegal as well. And it's a common language amongst many of our sort of geoscientists, data scientists, and developers. So, we've used Python in here in this project, but also a little bit of SQL as well. We tend to like using Jupyter notebooks, and as you've seen earlier today, these are pretty nice to use, running code cell by cell or line by line. Quite nice for sort of debugging and experimenting with code and building things up. But you can also extend Jupyter notebooks quite easily with a number of other open source tools. So you can make sort of dashboards with something called Voila, which essentially turns your Jupyter notebook into a little mini dashboard. So you have all of the markdown cells and outputs, as well as visualizations and everything else. You can also add things. I think Sebastian also showed this as well, that you can have widgets, essentially clickable buttons where you can interact with data inside the notebook, and Voila will also pick this up. So you can make a nice, simple user interface if you want to have a job done. Particularly in the case of someone who may or may not have so much Python experience, it's a nice interface to use. We also use Plotly. This is fantastic for displaying data. I showed you before an image of one of those interpretations. Plotly can show us it nicely. We have a really great, pretty well-known or very widely used library called scikit-learn, and this contains a number of different machine learning algorithms that we can use to actually develop a machine learning model or train one in order to automate our processes, labeling our interpretation. Finally, I'll talk a little bit about model evaluation, checking that our machine learning model is doing something logical and sensible and achieving what we want. So we can actually go under the hood and see what's going on, what is affecting that model, what parts of our metadata are actually driving that model to its predictions, and then we can critically evaluate our machine learning format. And that's a really nice, neat package called Shaposh. So the first task is to create a training data set. So our task here is to have a machine learning model that is going to classify our interpretations as good or bad using some relationships from the metadata. But in order to do that, it's a supervised learning scenario. We need to create a training data set. So we do have to manually label some of our interpretations from our database. And we just want to create a nice, simple user interface in order to do that. So I'll show you in one moment how this works. But we have a simple one where we can go to the next horizon, have a look at it, look at its metadata. An expert can then critically evaluate if this is good or bad. And what's important to consider is that we need a fair amount of this training data in order to train our model successfully. But it doesn't have to be, when you're considering, say, tens of thousands of interpretations, you don't need to have such a large database, such a large training set, but you do need something pretty decent size that's pretty representative of the rest of the database as a whole. And it's good that your interpreter here, defining what's good or bad, is quite consistent in how they do that. Yeah, so I'll just quickly show what that looks like. I have a Jupyter notebook here where the code is actually sitting in. We can connect to our database, and we're using this package called DBC, where we have we can use a bit of SQL and extract data from our database. I don't want to show too much code here. What we can do is we can launch voila, and this is that package that turns our Jupyter notebook into a simple dashboard or sort of user interface here, where we have all of that markdown cells explaining what's going on. And we have our nice little user interface here, where we can skip through our horizons. We can scan through the metadata. I can see that I actually did some labeling here before. I'm not going to change any of the labels right now. This interpretation seems to be lacking quite a lot of data. I can't really see much from this. This is previously classified as bad. You can see that it's Hilda that labeled that, and so on. I could change it if I want, but I agree with that. I'm not going to change anything. It's pretty neat that we've got just some simple open source materials to create a user interface that our expert can actually label our data. Once labeled, we can then move on to model training. And it's kind of typical that we would take several different models to actually just explore how different algorithms are working. What we do is we pass in that manual label data set, so we have the label good or bad, along with the metadata. Our model is going to learn the relationships between the metadata and the labels on our training subsets where we've manually labeled everything. And then what we can do is we can save out that model with all of its coefficients, if you like, or weights and biases. And we can save it down as a pickle file. That's something serialized that we can then pick up in another notebook, send to someone else, or use how we like. So it's a really nice way of just saving out the model properties so we don't have to train each time. But we can actually then apply this model to all of the rest of the data in the data set. So let's, for example, say we had 70,000 interpretations. We could manually label several hundred of those, perhaps. That's not going to be too much of a time-consuming task. And then we can apply that to all the rest of those thousands of interpretations in a matter of several seconds. So that's really automating that process and making it. You can also return not just the prediction, but the prediction certainty. And this value gives a good, strong indication of you know, how confident the model is in its prediction. And it gives some transparency of that model performance. Now, before we just use some of this demo data from Tracker database, and we did some manual labeling for good or bad interpretations. We can see that around 13% were bad and 87% were good. But now applying that model onto a small subset of data, we can see that our predicted label distribution is somewhat different. So it's somewhat 50-50 between good and bad. There could be reasons for this. Maybe the model is not performing so well, but it could just be that our manually labeled data set was not actually that representative. So we can get some good model evaluation, making some own custom plots just to check how things are going. But we can also use ChatBash. This is an open source Python package. And what this does is uses some algorithms which can calculate the contribution, for example, of different metadata that they have in driving a model prediction. So this is based off Shapley values. So what we can do, receive is a local explanation for each prediction. So every single interpretation that we have predicted the quality of, good or bad, we can see which pieces of metadata were actually driving that prediction. So we can see that defined area is particularly important, as well as point density. Total area was a little less important. This seems fairly logical. Maybe just to give an analogy on how this is working, this algorithm essentially looks at the contribution of each piece of information on the prediction. So to have an analogy, you could think of, say, a sports team, and we would be looking at that sports team, each member of that team's contribution to the overall score of that team in the game, and therefore we would see the contribution of each one of these pieces of metadata in that prediction. We can also get a global importance, so we can see how each of these pieces of metadata are affecting the model performance for all of the predictions. So it's averaged over all the predictions. That would be much like the contribution of the player, not just in one game, but over across all season. And of course, we can use this dashboard to flip between different predictions and get a little bit more understanding about how our model is performing, why it's making those predictions. I think it's particularly important to have this kind of transparency in machine learning, so we can build trust in what's actually happening under the hood, so that it's not black box, but glass box machine learning. So in summary, we use Python and a number of open source libraries to create a very simple interface so that a user could label good and bad interpretations. So this is just one small subset of the total database, just to create that data to train our machine learning model. Machine learning model was then trained, and a subset of that data was manually classified. And once that is trained and we're happy with that model, we're able to then apply it to the rest of the database, thereby automating the labeling of the rest of the database, which could be many thousands of interpretations in pretty fast time compared to someone manually doing. It's also important that we critically evaluate the model performance and have some model transparency so that we understand how and why that model is predicting whether our interpretations are good or bad. So we can build some trust. We can always go back. In theory, it would also be possible to overwrite this and manually enter something that was so important. So thank you very much for listening. And thanks to Tonje, and thank you to Kethel and Haley who are listening to this.
All right. Thank you, Tonje. Thank you, Thomas. We have one question from Chinmay Batve to you, Thomas. I think the question, I don't know what slide it refers to. The question is this a logistic regression model or decision tree model?
I believe this was a gradient boosted tree-based algorithm.